arguments. And this led to this rather intriguing discussion. So the first one, and many people still love this one, says, well, the moon is getting hit by a lot of cosmic rays. These collisions are even more energetic than the ones we get at the collider. The moon is still there. It hadn't been sucked into a black hole, haven't exploded the vacuum or turned into strangelets or Higgs bosons. Well, hence the Large Hadron Collider is safe. Is this argument correct? You can probably guess that I don't think it's correct, because the problem is, of course, that the collisions on the moon are actually not exactly similar. Because the moon is stationary compared to the particles, in the accelerator they're actually moving together at high speed, but the average velocity should be zero. So there might be that we get a lot of black holes out of the moon, it's just that they go out into space. So in the Hadron Collider we might end up with a stationary black hole. Fortunately, other people have come up with an argument against it. So this is Arnold Dar's extended argument. So basically they say that, okay, it's similar, but you might get fast-moving, weird particles that could be dangerous. These ones would be slowed down in interstellar space. Various physical reasons for this, which I can't really put into the slide. If you have these particles, well, when stars form, they would have these particles in them. And if these particles are able to eat planets rapidly, they should also be able to eat stars rapidly. Hence, the stars would be blowing up or doing something like supernovas. We can measure the number of supernovas, and we can get an estimate of how likely these particles are. And lo and behold, well, the Large Hadron Collider, it's safe. That's great. Except, of course, that there is another little correction you need to do. Because actually, if there are a lot of large explosions going around, they wipe out potential observers. So, Max Tegmark and Nick Bostrom, they wrote a little Nature paper where they demonstrated that actually, if the universe was really dangerous, we should expect Earth to have formed very early, and we should have evolved very early, because there are not going to be that many observers around at late times. So they based this on astrophysical models and the Earth's age and various data, and created a nice little correction. So that kind of reinforced the argument, but it also found a pretty nasty flaw in the argument. And now this puts us in a rather precarious situation. I don't think anybody in this room actually thinks the Large Hadron Collider is dangerous in any practical way. But scientific arguments doesn't seem to hold up that well. Actually, it's an interesting problem, but they seem to be wrong an awful lot of the time. When you try to do an argument yourself, of course, obviously you get to notice all of your flaws, and then the nasty reviewers claim to have found flaws. That's usually because we're wrong, of course, but occasionally we do find flaws. And then you look at scientific journal and notice that the retraction rate of many journals, where people actually withdraw papers because we found a serious flaw, well, it's not non-zero. It's actually on the rate between 1 in 100 and 1 in 1,000 papers. And we know that we make simple calculation mistakes at a surprising regularity. I could go on and on about the mistakes we make in calculations, models and so on, but it seems that it's very likely that at least one paper in 1,000 or one argument in 1,000 is wrong. And that's problematic for this kind of argument. Because at the start we have this unknown uncertainty. Is the Large Hadron Collider dangerous? Dar and et al., they write their papers and show, okay, this is how the total likelihood that it's safe, and then there is a small risk. This is of course not to scale. This is ridiculously small. So we should be feeling quite reassured. Except of course that there is a certain chance that the paper was wrong. Again, this is not to scale, because this should be about 1,000 of this, but it's going to be pretty big compared to that one, which means that the reduction in risk we got from hearing this nice argument isn't as big as we should expect. You can compare this to a situation where you're on a kind of country fair and there is a lottery going on, and you think that, oh, it looks like 1 in 10 chance of winning. Then your nephew tells you, no, I've been checking. It's a 1 in a million chance of winning because it's a rigged lottery. Now, you might believe your nephew completely because he's an expert and he's very good at rigging lotteries. In that case, you should just update your probability expectation directly to 1 in a million. It might just be that your nephew is just making up nice stories. He's just 5 years old and likes saying things like that. At that point, well, you should probably adjust your probability downwards a bit, but not all the way. So the interesting thing here is that we're kind of the same situation here. So there are ways out of this. So this is accidentally how it happened. So Mangano wrote in the bigger paper about why black holes are unlikely. And he essentially has three different arguments. Basically, black holes would evaporate due to Hawking radiation, and to be dangerous, they would also need to do some charge neutrality. I never really understood that part of the argument. And then the last 50 pages of this pretty big paper is about why they also would blow up in white dwarfs and neutron stars. And we see a lot of white dwarfs and neutron stars, so we don't need to be worried. I also found another paper arguing on information theoretical reasons that really small black holes can't absorb particles. It's a very amusing argument. I don't really know whether I believe that because it's really far out there. But now we see here actually 4 independent arguments. These ones, if one of them is wrong, it doesn't matter because the other have a pretty good chance of being right. There is 1 chance in 1,000 that there is no Hawking radiation, perhaps a bit more. But that still leaves us with pretty good protection from here. If these arguments had all been tied together into one argument, then they would have failed together. But they're actually independent. And this makes it possible to be very much more reassured. Because if when 1 chance in 1,000 times 1 chance in 1,000 times 1 chance in 1,000 times perhaps 1 chance in 1,000, well, that's actually 1 chance in a trillion. Okay, I think I can live with that kind of security assurance. It's a bit like
probabilities aren't independent.
Yes, that's the problem. So in this case, I think they are independent. I think I need to do a really careful reading to actually check it. So, for example, the physics data here, I think they seem to be pretty different actually. But if we're not completely independent, then the protection becomes less. Not directly zero, but smaller. That actually sounds like a great paper for me to write when I get some time, actually. It is quite fun. Maybe that can make me persona grata again in Switzerland. But basically, having these separate arguments, it's a bit like slicing up that unknown section again and again and again. This way, we get actually a very much more controlled unknown area. And this also shows that there are ways of doing robust reasoning, even when we know our own reasoning is pretty fallible. There are other tricks you can do too. For example, you could set up a red team, blue team. You could have a gang of physicists trying to figure out new disaster scenarios, and other physicists demonstrating why that's unlikely. And then the red team come up with flaws in that argument and so on. This is a standard procedure when doing security work. And it's actually a pretty good way of figuring out robustness of arguments. That's not normally something you do in theoretical physics, because in theoretical physics you're out with, you have a very different epistemological aims. But in terms of safety, you might actually need to do this. Okay, so what should we be doing about this? Well, overall, it seems to be a lot of very interesting things we can do about it. We should obviously notice that uncertainty exists on a lot of different levels. We have epistemic uncertainty, we haven't got all the data. And then we got the more fundamental, ontological uncertainty. We don't understand the systems going on. So in the case of the pigs, well, we simply haven't got much data, but we have a pretty good idea what the viruses are and how epidemics work. We won't be really surprised by that. In the case of black swans, we have a problem that we don't really understand the physics going on behind it. And the dragon's case is that we're really certain that we don't know what's going on in the physics. But we can still bound that by using robust arguments. In many cases, we can also do a lot of very clever things simply by doing a bit of preparation. In Japan, they have a lot of disasters, and they also have a lot of very good disaster readiness. So the Shinkansen rapid transit system has a seismograph system to notice earthquakes. They can't predict earthquakes. The Japanese have been trying for ages, but it simply doesn't work for various technical reasons. But you can actually notice it when it happens. And then, of course, send a signal at light speed along the system to tell the train to slow down before the tremor has a chance to get to them. It might be a case of a few seconds warning, but that's actually quite enough to reduce the risk of fatalities. I did a little study with a friend about a meteor impact in a big city, and it turned out that if you had 1 hour warning and could just tell everybody, stay indoors, prepare for an earthquake, hide in a cellar, you would have half the number of fatalities. A lot of people would still get killed, but that little amount of preparation would actually have a quite enormous effect. Then there is this problem that we tend to be seduced by elegant mathematical models.